Hello, everyone. Welcome to another Q&A about the future of science and technology. And I see there are a bunch of questions saved up here. Let me take a look at them. Let's see, there's one pretty practical one from Brady here. Do you foresee the Wolfram Notebook Assistant breaking out of the notebook in the future? It will be a great general voice assistant which knows about me personally and works like Iron Man's Jarvis. Well, our Wolfram Notebook Assistant is making use of a bunch of our content and technology with an interface of an LLM to provide kind of a conversational way to make things computable. It's kind of I think I mentioned this in a previous live stream, going from X to computational X for all X, so to speak. And really the focus for the Notebook Assistant is to assist people who are trying to be computational with Wolfram language. It's actually part of a family of products that we are developing that deal with different kind of form factors of usage of computation. So this is one where kind of the anchor is the computational language, the Wolfram language, the stating things in precise computational terms. There are other things that we're looking at that have a more direct talk to it, walk up to it, consumer kind of feel. It's sort of the challenge is how to set that up. Then when it comes to actuating sort of things in your environment with a system like that, there are all kinds of questions that important to think about, well, okay, you connect it to your file system. What happens if you say something and it interprets as delete all my files? How do you deal with that? What's the right way to do that? Is that something that is relevant for us to be tackling, or is that something that is more a generic consumer kind of thing that's more tied into computer operating systems and so on, and less something relevant to our kind of mission of kind of making things computational that are more sort of an intellectual level? So a few comments about that. But yes, we have a lot of interesting things going on there. The most immediate thing that will happen is the ability of Notebook Assistant to look at files in any format, basically, and to think about them computationally. And that will be, I think, a very useful thing coming soon. Let's see. There's a question from Samir. People on Mars by 2030, with a question mark. I really doubt it. I mean, on exactly that time frame. I mean, the fact is there are these 2-year windows of when the Earth and Mars are sort of near enough by in their orbits that you can sort of send a spacecraft without having to send it all the way to the other side of the sun type thing. So there are particular discrete times at which you can launch missions to Mars, and the question of when it will be possible to have people go there, it's complicated. There's a lot of technology that has to sort of come together and work to keep the people sort of alive and happy during the trip to Mars, with all of the kind of radiation that they encounter, all the kinds of bring enough food, to some extent, I think those kinds of things. And once you get to Mars, you're kind of stuck there for a while. You're not coming back, certainly until there's another 2-year window, another window every couple of years to make it back. And it's a question of, can you sort of improvise things enough? Can you send enough stuff to be able to improvise things to sort of keep alive in an environment that is really a pretty harsh environment? I mean, it's kind of it's worse than Antarctic 2.0, so to speak, as a place to hang out. So, there are a bunch of challenges there. It's something that I find interesting in terms of the role of science and technology in society. Is I'm not sure whether there is a pragmatic kind of thing that will be achieved by having people hanging out on Mars, but it's sure good as an aspiration. And that's, I think, an important role for science and technology in the world. Is it is something that kind of it's a shared thing that is kind of aspirational, whether it's science figuring out something about the fundamental theory of physics, figuring out about the sort of vastness of the universe, the smallness of the elements of the universe, those kinds of things that sort of give one a certain sense of awe about what's out there in the universe beyond kind of the details of everyday life, so to speak. That's an important piece of the story. Of course, there are pragmatic things, whether it's kind of giving us better gadgets or whether it's improving medical kinds of things. There are those things too. But I think that the kind of purely intellectual kind of sense of awe made possible by kind of deep science is something significant. There's also a certain aesthetic associated with kind of deep science that's important. When it comes to kind of the practical, things like let's go mount an effort to get our species to another planet is kind of a great aspirational thing, regardless of whether the result of that is, it has this economic value, or we can get sort of cool Mars rocks that are going to be really interesting for any particular purpose. I think that's the aspiration alone is important, and as a justification not only for these kinds of technological initiatives, but also for basic science initiatives. And it's worth, as one sort of thinks about the role of basic science and things like, why should we do basic science? Should we do it because there's ultimately a flow through to economic benefit, or should we do it just because it has a certain enrichment of our existence as a thing to know and a thing to aspire to, so to speak? So, in terms of let's start off with expecting a moon base, which I think is plausible on that time frame, and it'll be interesting to see what people sort of find to do with the moon, so to speak. It kind of reminds one of the early days of flight, where it wasn't clear, the idea that there will be passenger planes, freight planes moving cargo around, aerial reconnaissance, bombing from planes, all these kinds of things. These all had to be kind of discovered as applications for planes. I think now that we're seeing sort of the cost of putting things into Earth orbit going down, we're seeing more and more things that it becomes clear can sort of happen in Earth orbit, whether it's kind of communications, more and more consumerized communications from there, more and more consumerized remote sensing and so on. And there'll probably be more as the price comes down and the density of things in orbit goes up. There'll probably be more things that get discovered as, yes, you can do that, and it makes sense to do it. It's often hard to imagine these things in advance. It's much easier once sort of the capability is there and one's starting to sort of pick away at other things, it becomes more obvious what will be possible. I mean, on the moon, people say, I think a little bit strangely, that put all the heavy manufacturing on the moon and just sort of vent all the gunk. Don't have it hang out in the Earth's atmosphere. Vent all the gunk out into the solar system. I'm not sure that makes that much sense, but who knows? But there certainly are things that are going to be. There'll be things probably. There are things that will turn out. Oh, if you have 1/6 of gravity, this is a thing that you can manufacture really easily. Or if you're on the far side of the moon, and it's very any of the sort of pollution in terms of radio energy from the Earth isn't there, and you're setting up a giant radio telescope, you don't have to worry about having everybody in the neighborhood switch off their cell phones, so to speak. Well, at least for now, there aren't any cell phones on the far side of the moon. So I think that's a nearer term kind of thing. Let's see. There's a question here from Susan talking about the future of our physics project. The future is, I think, extremely bright. I think So just sort of to recap, this is something which really came together at the beginning of 2020, right at the same time as the pandemic was rolling in. Our physics project, understanding kind of what the underlying structure of the physical universe is. And I have to say that in the last 5 years, I have become ever more convinced that yes, we nailed it. This is really the right way to describe what's going on. It's not the only way to describe it, but other ways of describing it will be equivalent to this way of describing it. They just may or may not be more convenient for people to understand. But this way of describing it starts by saying that all there is in the universe is this giant network of elements of space, sort of discrete atoms of space related through this network, this hypergraph, and that all features of the universe are features of this giant hypergraph, whether those features are sort of things about gravity, whether those features are the presence of an electron or a black hole or something else, they're all just features of this hypergraph. And then there's the question of sort of the dynamics of this hypergraph. And the thing that I knew actually even in the early 1990s is that kind of the collective effect of that turns out to be, with certain conditions, turns out to be the kind of effect in space-time that corresponds to Einstein's equations for gravity and the structure of space-time. The thing that became clear only in late 2019 was that this same kind of underlying framework can kind of inevitably leads to quantum mechanics. I kind of knew versions of that in the 1990s, but I didn't really believe it well enough to really lean fully into what's possible there. And we sort of understood that. Now, what's happened since is okay, so the things that sort of led to the possibility of the physics project were my efforts in new kind of science and an understanding how simple programs can behave in complicated ways, in ways that kind of correspond to what we see in nature. Also, a lot of the kind of underlying formal theoretical structure of simple programs and how they behave. And I think the thing that I've seen is this sort of progressive development, both of scientific ideas and of tools, particularly Wolfram language tools, to just, as a practical matter, deal with the kinds of things that we need for the physics project. And that's been a long, long process. I mean, I've been at this now for more than 40 years. It's more like 45 years now. And what I can see is that the physics project was only possible in these times because of that strange sequence of developing technology, developing ideas in science and so on, building this tower that eventually let us get to the physics project. So the question of where do we go next? Well, it's pretty clear where we go next. Getting there is a lot of work. So let's understand what we need. We need things about sort of formal theoretical development. We need ways to understand this thing made of a hypergraph, this limit of a hypergraph. What kind of a mathematical object is that? It's something that hasn't been studied before. It forces one to go beyond traditional geometry, traditional calculus, to what I've been calling infrageometry, kind of what you get when you make a space not out of something which can be patched together out of little pieces of Euclidean space, little pieces of space as we normally describe it with coordinates and things like that, but instead a space that can be gotten as this limit of this hypergraph. That's a different kind of underlying structure for geometry, underlying structure for calculus. Kind of, it's weird when you realize we have to know about, calculus with 3.3 dimensions, 3.3 variables. That's something that just hasn't really been looked at before. We need to build a kind of formal mathematical theoretical structure to handle those kinds of things. We're working on it. It's hard work. I have to say, on one rather simple part of that, of the questions that come up there, a number of years ago, I was asking a leading mathematician, graph theorist, about one of these questions, and he said to me, come back in 100 years, and we may know something more about the answer to that question. So the timescales of this sort of mathematical development can be very long. We're trying to push it vastly faster than that, and it's going fairly well. But it's just worth realizing that in the natural course of things, the development of the kind of mathematics that's needed is kind of a century timescale kind of thing. we're trying to do it vastly faster than that because I want to be around to see what happens. But in any case, so that's on the one side is sort of formal development. On another side is kind of simulation. And that's a place where there's a question, can we actually simulate things about space-time using our discrete models? Actually, Jonathan Gorard, who's been involved with this project since the very beginning, has been doing lots of stuff in that direction and making kind of practical simulation tools based on the physics project to study things like black hole mergers and so on, and trying to see when there are effects that could be sort of indicative of discreteness of space-time and so on. So then then there's quantum mechanics, and we've done a lot of work on understanding kind of the relations between quantum mechanics in our models and quantum mechanics that's been known before. Actually, very recently, I think, not sure quite yet, but I think maybe we made kind of a big breakthrough in understanding how quantum field theory sort of fits into our models, and particularly in taking these things called Feynman diagrams, which are sort of very widely used in particle physics, invented by my former friend Dick Feynman before I knew him. But I certainly talked to him about Feynman diagrams a lot. And in my own kind of trajectory in science, Feynman diagrams are sort of the big complicated thing to calculate with in particle physics. And one of the things that got me involved in doing mathematical computation with computers was computing Feynman diagrams. And I'm sort of a big Feynman diagram enthusiast when I was a teenager and back a while ago, so to speak. And it's kind of fun to see that it looks like, we'll see exactly how it works out, that Feynman diagrams turn out to be sort of reinterpretation of them, turns out to be a very central thing in seeing how quantum field theory plugs into our physics project and its models. We'll see how that works, but it's right now it's looking really promising. What I've noticed is that we've taken kind of the formalism from the physics project and I've applied it to all kinds of things, whether it's studying the structure of games and puzzles, whether it's understanding things about observers and their character, whether it's understanding things about biology recently, things about distributed computing. What I've found, which is not obvious that this would work this way, is that every one of these things that seems like it's distractive from sort of making immediate forward progress with physics and nothing but physics actually comes back to inform what we're doing with physics. It's really kind of interesting that way. The straight path is not the path that leads you to the best result. It's something where understanding things in these often deeper ways by looking at these kind of things that seem irrelevant. It's like, why does studying biology and the foundations of biological evolution, what does that tell one about physics? I'm realizing actually it gives one a lot of insight about how observers work in physics and so on. And we're about to see that sort of come back to physics, even though what came out to biology sort of was a spin-off from the physics project. So it's been sort of an interesting thing. And I'm hoping in the next year to get back to things which are sort of very much mainstream parts of the physics from the physics project. I think the thing that is sort of the exciting thing to aim for, well, there are really two things. One is the development of formalism, maybe three. The development of formalism, the development of simulation tools, and the figuring out of kind of effects which will allow us to connect the physics project with actual experiments, which if we're lucky, can be done now. If we're unlucky, they're 200 years away. But if we're lucky, there'll be experiments that we can sort of immediately do. My current sort of best sort of efforts in that direction, mostly astrophysical experiments. I have this suspicion that dark matter isn't matter at all, but is a feature of the structure of space, much as heat, which people imagined was a fluid back a couple of hundred years ago, turned out to be actually a feature of the microscopic structure of matter, the motion of molecules and so on. I kind of suspect that dark matter is sort of misnamed as matter, as caloric fluid for heat was misnamed as a fluid. And so trying to understand that and trying to understand whether we can see something that we've known about for 100 years about sort of dark matter and its effect on the rotation curves of galaxies and so on, whether in fact that is a sign of something that we should be able to pick up, that is a sign of kind of the underlying discreteness of space and the structure of these models. That's one example. There are a bunch of others about dimension as a dynamical variable, kind of the changing of dimension, not just 3 dimensions, but little fluctuations around that, the effects of that, those kinds of things. But I suspect that there may be some effect out there that's just like, oh, we never thought of that. You know, if you have a neutron star really close to the central black hole of a galaxy or something and doing exactly this, there's some weird effect that one hadn't thought of, which when one thinks of it in terms of our models, you realize, well, let's calculate that. And oh, it does something really weird. Let's go look for that. You know, it's worth remembering in the case of general relativity from 1915, there were some effects that were like not obvious to go look for, like, for example, the extra bending of light around the sun, or the precession of the orbit of Mercury around the sun, those kinds of things, and sort of the much bigger prediction of general relativity, namely the existence of black holes, was something that took, oh, really until the 1960s for people to understand and not be confused about. And that's sort of a cautionary tale in terms of the model was there, the model was clear, the implications of the model are hard to work out and really required a lot of kind of careful interpretation of, well, what's a true singularity versus just a mathematical kind of coincidence of, you know, computing 1 over x more or less as x goes to 0, those kinds of things. Is it real? Is it a physical singularity? Is it mathematical? How does that work? That took a long time to resolve. And the other thing which Einstein kind of missed was his general relativity theory would have naturally predicted that the universe should expand. But in his time, he was like, but of course it doesn't expand. So he had to put in sort of a hack, the cosmological term, to avoid that. There may very well be things in our physics project, which again are things where it predicts something which seems so outlandish that one would want to say, oh, no, let's pull back from that. I have to say, one of the things that's kind of one of the most exciting things about our physics project is that in the last 5 years, there has been no inducement to add any hacks. It's just, this is the model, and this model, while it's very hard to predict its consequences and to connect it to what one can see in existing physics, it's not like we're patching it. It's not like we're saying, oh, but we have to avoid the expansion of the universe, so we have to put in this patch or anything like that, which is a really, really good sign for a model. That's really a great kind of qualitative sign for a model. The model that what you put in is tiny, what you get out is huge, and there are no patches that you have to add. That's a really good sign. Now, the other thing from our model is kind of the sort of philosophical implications, and particularly leading to the Rulliad and leading to thinking about observers and consciousness and the role of consciousness in physics and the kind of observer dependence of the laws of physics, all these kinds of things. Those things are both very interesting in their own right, but also I can see how those feed back into just understanding what it is you go and look through a telescope and observe, because kind of having that idea of what an observer is like is kind of a key aspect of knowing what you set up. I mean, for example, when you set up sort of the structure of space-time and you're trying to make something which corresponds to 2 little black holes, let's say, then it's something where getting kind of the structure so that it is consistently what we would call 2 little black holes is really quite non-trivial. But that story of how you set that up and what makes sense to set up there is very much a story of what observers like us are like. So those are a few things, but I would say that on the one side, I'm really keen on sort of the astrophysical kinds of things and understanding dark matter, understanding dimension fluctuations of the early universe, understanding some sort of high energy phenomena in astrophysics. On the other hand, I'm keen on the quantum mechanics side this thing that I'm working on right now that might be a little bit of a breakthrough in sort of quantum field theory will be interesting because it'll allow one to calculate a bunch more things in quantum field theory, which is a very difficult area to calculate things and much more difficult than the theory of space-time and so on, which is already very difficult. But the other big thing is, can we see the effects of our model on sort of deviations from quantum mechanics? Quantum mechanics is sort of a theory that's sort of in a box. It explains a certain set of things, and then there are things where it just sort of says, and then, well, particularly when it comes to measuring things in quantum mechanics, just like, and then it happens. For the last nearly 100 years, one's had a formalism for quantum mechanics, which says, well, there are all these little quantum effects, and we know a bunch of fancy mathematics that describes those effects. And then somehow we come in and experience these things, and that's just this mathematical operation that goes ka-thunk and applies itself to this sort of inner quantum process, these inner quantum processes. And how that measurement process really works is something that is important for understanding what happens when you try and apply quantum mechanics to things. It's kind of, the qualitative picture is sort of in the quantum process itself, there are many threads of history that are going on in parallel. But when we come to experience all of that, we humans like to focus everything on a single thread of experience. That's sort of one of the key things that our consciousness does, so to speak, is to say, yes, definite things happen in the world. How that focusing works, it's a dynamics of how that works, which we partly understand in our physics project, although I'd like to understand it better. So one of the places where one kind of starts to see that is in quantum computing, where one is trying to make sort of ever sort of more detailed use of the phenomena of quantum mechanics. And sort of a question of what's involved in this process of going from the quantum threads down to the human experienceable definite outcome. And that's been sort of the measurement problem of quantum mechanics forever. We're starting to see how that can be understood in terms of our physics project, but also we're starting to see sort of experiments that poke at that in the things about quantum computers that actually are the things that paradoxically are the places where people just want to push that aside. Because when you go to a quantum computer, you want to kind of get it to do some exciting computation. The fact that there's noise, there's things that are hard to measure in it and so on, that's all, oh, we want to get rid of that. We want to sort of squash that out. I think that's the most interesting physics, probably. And I have this hope that actually the sort of quantum computing experiments have been done carefully enough that we can actually use them to see things which are kind of seeing through to foundational aspects of the universe that will allow us to understand sort of the correspondence with things that we're seeing in our physics project. So one of the things I'm sort of hoping is to really go and understand. It's sort of a funny thing. I'm trying to understand exactly the things that people who are trying to do quantum computing for sort of technological purposes exactly want to squash out and ignore. It's kind of like the idea of, if you are building telescopes and you want to build a better and better telescope, you keep on polishing the mirror better, but still there's an ability to increase the resolution of the telescope beyond something. If you're interested in the physics of light, knowing about that is critical, because then in principle you can compute the wavelength of light, you can understand diffraction, things like that. The analog of that for quantum mechanics is this phenomenon of the maximum entanglement speed, which shows up in our models of physics. And if it would be a wonderful thing if it was possible to compute the maximum entanglement speed from existing measurements that have been done in attempts to make better quantum computers. And if we know the maximum entanglement speed, it will imply the elementary length and the elementary time, and we'll kind of know the discreteness scale of the universe. What we don't know right now is the discreteness scale of the universe sort of big enough that we can seriously expect to do experiments in the next few decades that can detect it, or is it really out of range? People were lucky when it came to molecules, when they were sort of discovered in the late 19th century, beginning of the 20th century, that molecules are sort of big enough that instruments like microscopes could see Brownian motion, things like this, that kind of the scale was sort of close enough to human scale, even though molecules are really small compared to human scale, but there were things that were close enough that it was possible to actually do the experiments and see those things at that point 120 years ago or so now. So I don't know whether we'll be lucky in that way, but I want to really find out, even if we don't know the elementary length, even if we don't know, is this an experiment that we could actually do now? I want to kind of see whether we can find that out, and I'm sort of hoping to look at that. Now, I will say that the sort of the sociology of our physics project is interesting, because what we see is that the project kind of plugs into all these other areas of mathematical physics, all these things that people have been studying for a few decades or so, which have often not been very well grounded or connected to things that you could actually expect to do experiments about. And I think that seeing the kind of formal connections between that and our physics project, that's an important thing. And it's an important thing sort of sociologically, because it brings communities of physicists who've been working on all sorts of interesting things, sort of connecting to the things that we're doing in the physics project. The physics project provides kind of a hub for thinking about a lot of these different things in a consistent, formal kind of way. And I think that's one of the things that I'm sort of hoping will really pick up. There's a little bit of this that's happened, but there's an awful lot that could be done, is making all these bridges and understanding, what exactly is the correspondence between our physics project and work that's been done on spin networks. Or Well, hello again, everybody. Sorry about that. Talking of the future of science and technology today, we just set up a new, fancier system for doing these live streams, and the computer that was running it just completely froze, and froze in a way that was so frozen that it could barely even reboot itself. Anyway, now I'm using a different computer, and we're back. And I think I was talking about, let's see. Oh, is this even today's questions? Here we go. Yes. We're talking about the future of our physics project. I'm not quite sure where I got cut off, but I think I may have been talking about quantum computers, and perhaps somebody can tell me where we ended and whether we talked through quantum computers and trying to detect the maximum entanglement speed through kind of the parts of quantum computing that people kind of want to sweep under the rug because it's like, oh, that's noise, that's imperfections in what we're doing. I think that's going to be interesting physics, and I'm hoping it's going to tell us a bunch of things about our physics project. But let me keep going here. Let's see. Questions about from Tori, what's the future of an observer? You know, it's interesting because as we become more sophisticated observers, we notice other features of the universe. Whether there was a time when we didn't know about radio, in the late 1800s, we learned about the idea of radio waves, electromagnetic waves, radio, and then there was a whole other facet of the universe that we could be exposed to. In recent years, we've been able to detect gravitational waves, another facet of the universe that we get exposed to. But not only are these things that where we're seeing some different aspect of the universe, there are also things which we don't even think about if we don't imagine being able to experience them. And I think that's a thing where that's true across lots of areas of science. Kind of as paradigms advance, there are new kinds of things we can talk about and new kinds of things that we can do science with and reason about, so to speak. And so that's kind of part of the progress of sort of intellectual development of our civilization, is these sort of new paradigms, which are also connected often to new things that we can detect experimentally with actual devices and so on. So those are kind of things that I think the future of observers is to be able to observe more kinds of things and to have laws about aspects of our universe where we're not even aware of that aspect of our universe right now. If we hadn't known, having laws about gravitational waves is irrelevant unless you have kind of the ability to connect with and the idea of connecting with gravitational waves. And that's true also at a theoretical level. And I think there's some really interesting things that I'm hoping to see. The things that I've studied in mathematics that are kind of things where you're sensing aspects of mathematics very different from the way that you normally sense mathematics. You're sensing much more global aspects of mathematics than you have sensed before. And that leads to sort of a different kind of observer. Same with biology, for example. We're used to certain aspects of biology, the things that affect sort of the actions of organisms like us and so on. But when it comes to the microscopic aspects of biology, it's just very unclear what things we look at, so to speak. Do we measure the concentration of this or that chemical, or is there some form of sensing things, which once we know it, we say, oh yes, of course, that allows us to kind of understand biology in a different way, make different kinds of laws for biology. Just like when the digital nature of DNA was discovered in 1953, there was sort of a different way of thinking about aspects of genetics and biology at that time. So let's see. Oh, so I'm being told when I was talking before about the future of our physics project, I just kind of got cut off when I was talking about the dynamics of our physics project kind of plugging into all these different areas of development of theoretical physics, all these different approaches to sort of foundational physics. And the very interesting thing that became clear when the physics project we were first doing was that what we have is something that is sort of a hub and a foundation for a lot of different developments that have been made over the last few decades. And what we're seeing kind of sociologically is kind of the plugging in of the communities that have been associated with those particular areas into kind of the things that are of interest from our physics project, whether it's the graph rewriting people, whether it's the higher category theory people, the spin networks people. These are people who've developed very great sort of technical work in these particular areas. It's been a little bit unclear how these areas relate to, for example, observable physics. Now our physics project informs that, but our physics project also provides kind of a different type of formalism that can be imported into these fields. The things from these fields can be imported into our physics project. I think there's a lot that is very promising, and I'm really hoping to see people really engage more seriously with this. And as we build out our Wolfram Institute effort, I think we're providing kind of an ecosystem for this to happen, for people to really make all of these connections, explain exactly how string theory connects to our physics project. And it does connect. And it's going to be something that is useful for string theory, and ideas that have developed in string theory will be useful for our physics project to make that connection with clarity. So let's see. Brianna is commenting, in many models of the universe, there are small variations that lead to division by zero, which leads the programmer to put in a fix. Could black holes be that fix in our universe? Not quite. I mean, black holes, roughly, the simplest case of black holes is something which in our physics project, they're places where time stops. In our physics project, the progress of time is the doing of computation, the updating of this hypergraph that represents space and everything in it by applying these rules that say, and if you have a hypergraph that looks like this, it will be rewritten to one that looks like that according to this rule. What can happen is there can be a situation where no more rules apply. So that means that effectively time has stopped at that place. And that's what happens at this singularity in the center of the simplest kinds of black holes. So that's an example of kind of how those things arise in our physics project. It's not really, I mean, I suppose you can say, what's the rate of progression of time? Well, it's zero in this case. And that you could sort of turn that into a division by zero type thing, but it has a somewhat different character it's a place where time stops, so to speak. That's at least one type of black hole. Let's see. Jimmy is asking, predictions for the future of science and technology in 2025. You know, it's often a lot easier to say what will happen than when it will happen. And some things, it's, I think an area where there's a lot of potential development is kind of AI-ish things. But I think we saw the big jump in kind of textually oriented AI already happened. We are sort of the connection between kind of AI and fundamental science is interesting. I mean, I can see that there is a lot of enablement in the same way that there was when web search came in. I mean, before web search, you could, as a person, I used to always do literature searches, sometimes with physical science citation index books, sometimes with online versions of that. It was actually pretty functional if you knew how to use those things. But then web search came in and it became a lot easier to do those kinds of things. One of the things with LLMs and so on is the ability to do what amounts to sort of find that piece of knowledge that was kind of hidden in some ways. So I've been interested recently in some things about the foundations of mathematics, and I've been interested in figuring out, has an axiom system of this kind ever been seen before in mathematics? And the LLMs haven't been perfect, but they've gotten some information on that. And it's something you couldn't find by just doing sort of a regular search, because the notation will be different, the characters won't be the same, but somehow the LLM essence is the same. Now, when it comes to sort of the assembling of kind of, it's kind of like, I'm stuck, where do I go next? What I found really useful is that I can take a pretty vague idea I have, and with our notebook assistant technology, that's kind of LLM plus a bunch of computation augmented generation techniques, plus a bunch of other things from our technology stack, with that kind of collection of things, I can be very vague and conversational and turn that into something that is precise and computational and allows me to kind of leverage all the capabilities of computation and a Wolfram language to make forward progress. And that's something I think we'll probably see more of. We'll probably see the sort of the flowering of computational X as more people get more access to the ability to make things computational. I'm not sure that's going to be a thing where there'll be drama, one day it'll be, a big announcement about something. I mean, that's or whether it's something more like what happened in the sort of arrival of programs as models of things, which is something I kind of started really pushing in the early 1980s, and it took probably 20, 30 years for that to become sort of the dominant form of modeling that's done. That was a slow process. It wasn't like one day you announce it and then everybody does it the next day type thing. So, I do expect it's sort of an interesting question. Well, there are always things where sort of there are experiments, there's theory. There's things where we have very powerful theoretical things to say, now we have to connect them to experiments. And then there are occasionally experiments that get done that just lead to very unexpected results. I mean, there will be things, one day somebody will figure out something like cryonics. It'll just be, oh, you do this and this and this thing, and then you can kind of sort of pause humans and sort of freeze them for X amount of time and bring them back again. One day that will just be a thing that one can do. There'll be a discovery of that kind probably at some point. Could it happen in a year? Yeah, it could happen. I think it's hard to predict. It's very hard to know when things will get discovered like that. Could one see something? Often there are experiments where people are saying like we're studying, like for example, for gravitational waves. I remember seeing the beginnings of those experiments in the end of the 1970s, and it took until, what was it, 6, 7 years ago before gravitational waves were finally observed. But it was really a path where you could kind of see it was going in that direction. The same is in something like particle physics. We come a little bit to the end of the road in terms of what one can readily observe with like particle accelerators. It could be the case that somebody observes some very surprising particle-like phenomenon in some other kind of detector. I am kind of skeptical of that actually, but it's possible, and that would be kind of a surprise arrival of something. I think it's very hard to. I mean, if one asks for the overall trends of kind of what's happening in science, in kind of I think that's a big story about different kinds of formalism for making theories of things that started with kind of used programs, now use this kind of multi-computational idea that's come from our physics project, ways to sort of think about formalizing things that give you a new way to kind of new paradigm for figuring stuff out. That's an important direction. I think that the progressive automation of experiments is another thing that has been sort of slow, and it's finally kind of catching on. And it's in life sciences, for example, that will be quite a change of no more manual pipetting type thing. And I think that that will, again, that's a methodological change. What it will lead to in terms of the wow discoveries, I don't know. But there are these sort of methodological trends that one can kind of see rolling in, so to speak. I think some people sort of imagine, oh, the AIs are going to take over science. I don't quite think so. What is interesting is to see where can tools best be used in science? So, for example, for myself, I've made immense use of computers in doing science. And one of the things that I figured out the beginning of the 1980s was you can use computers to do computer experiments. You can experiment on abstract computational systems and discover things and get intuition that way. I understood how to do that with computers and visualizing things and so on. And that's been what led to new kind of science, what led to eventually the physics project and so on. Now, there are other kinds of tooling, including AI and LLMs, where I don't yet really get how I use them to build another level of intuition about science, for example. I understand how to use them as practical tools, as a different kind of interface technology and so on. But in terms of using them to sort of build intuition in science, I haven't figured that out yet. I think that, for example, I'm just doing a project right now trying to understand, well, a proof that I did with automated theorem proving 25 years ago now, and which has never been really humanized. It's never been clear what the human interpretation of that proof is. And I'm sort of trying to understand that and understand the connection of that to things that AIs can do in areas like mathematics. I think it's a bit unclear. Now, there are things that become possible, like experiments in social science where the LLM is the proxy human. That's fairly interesting. I don't completely understand yet sort of how to really work that through. I don't really understand what the scientific questions that one should be asking in psychology, or for that matter, neuroscience are, because again, the sort of success of LLMs gives one a way to approach neuroscience that one hasn't had before. But the question is, the first level of question is, what's the question? In other words, if we say, I want a theory of psychology, what we'd like that theory to be able to say. If we want a theory of neuroscience, what kind of a thing would we like it to say? It comes up again, even in theories of biology. These are things which I don't think, some of these things might be wow, we solved it and, we announced something this week, but most of that is paradigmatic change, which is on decade timescales, not on the what used to be press conference type timescales. Let's see. Let's see. Ozzy asks, what's an area physics might leak into that will be unexpected in the future? Physics is this kind of approach to kind of making quantitative lots of kinds of things in the world. It kind of seeded many areas, from molecular biology to quantitative finance to some aspects of modern AI ideas, actually quite a lot of modern AI ideas. And I think this question of, can we make a physics of LLMs? That's an interesting question. Can we make a psychology of LLMs? What's the relationship between a physics of LLMs and a psychology of LLMs? We don't know any of those things yet. I think that's an interesting set of areas. I think the thing that's come out of our physics project is the fact that that same formalism, multi-computation, the Roolead, all hypergraph rewriting, all of that same formalism seems to be applicable to all these other areas, including machine learning, foundations of mathematics, probably economics, biology, and so on. And the fact that there is this kind of common formalism, common foundational formalism, means that you can expect to transport ideas that come from physics, traditional physics, through that common formalism to other areas, and from those other areas back to physics. These are things that, well, I've been seeing in my own efforts recently, lots of interesting ways to make those connections. More to come, I think. Sort of a personal question from Inky here. Will you ever write another book like A New Kind of Science? I think one 10 and a bit year project that is a single intense effort like that is probably about as much as fits in a lifetime, the length of life, given the lengths of lifetimes that exist today. I've been kind of, for me, it's just like a terrific experience that I find myself going back to looking at things in NKS, A New Kind of Science, pretty much every day. It's not like I built it and it's gone, it's irrelevant now. It was a thing of its time. no, it's a thing that is a foundation on which a lot of other stuff has been built. I mean, I've been sort of fortunate, or at least I've kind of planned it a lot that way, that the things I built, whether it's in technology and Wolfram language or in science, have been things that are kind of foundations for more things that I want to do. They're not just things that happened and now that's the past type thing. But I've adopted a slightly different rhythm of work where I'm putting out, and they're not short, but often 100-page kind of pieces of writing that are not as they're not as single coherent lump of new ideas as New Kind of Science was. The physics project is kind of similar to that, a little bit smaller in terms of the scope of the ideas involved. And that turned into, I don't know what it was, a 700-page book or something instead of a 1,200-page book. But it was something that was written much more quickly and didn't quite pack in as much stuff. I would say that one feature of New Kind of Science is that when I wrote it in the 1990s, the idea of making it a book was really the principal direction. And that meant that even though it might have 50,000 pages of content, I had to fit it in the 1,200 pages that you could still bind as a book. So that kind of constrained what one was presenting. Nowadays, I find it more, because we can put out sort of infinite amounts. Once we have kind of the framework that people can understand, it's like, well, you can click on this thing and you can follow it to that, and you can run this code and all those kinds of things. So it's a little bit of a different environment in terms of explaining things. I think that the kind of paradigmatic ideas of New Kind of Science are what they are, and they're a fantastic sort of foundation for a huge amount of stuff that I've done and that can be done, has been done by a lot of other people, and will be done in the future by lots of other people. And I don't think there's kind of a need for another foundation quite like that. The physics project and the things around it, the Rouliad and so on, they are another step in that foundational development. And I've kind of written about those. I don't think it needs kind of a thing with the 10-year commitment of a New Kind of Science. I will say that it has become easier, given the things I've already done, it has become easier for me to describe incremental progress. That is, I hope, fairly large steps of incremental progress, but nevertheless building on foundations that I've already defined, rather than having to kind of describe all of the foundations in order to get anywhere. Let's see. Lolly is commenting that I could pick blog posts and publish them as book. I do that quite a bit. I've many of the books, most of the books that I brought out in recent years have started as what one might call blog posts, although I don't know whether that's really an accurate way to describe them, because a 100-page detailed thing is a little bit on the edge of what one could consider a blog, so to speak. The style is perhaps more blog-like. I like the style of being able to just explain things. It's the same way that people used to do it in the 1600s when they first started writing technical academic papers. It's just explain stuff. You don't have to write it in this kind of formalized English structure that has become traditional in most areas of academia. Let's see, maybe one or two more questions, and then I should wrap up for today. Leo asks, how might LLMs enhance future scientific development? What direction do you envision for tools like Mathematica, given that LLMs can interact with humans without requiring them to know how to program? Well, I think I understand that really pretty well. I think the point is that in order to build kind of computational towers, you need to have kind of solid foundations. Yes, with words, I can make arguments, but I can't build the kinds of things that correspond to sort of deep computations that take millions, billions of operations to get to a conclusion. That to get that set up, you have to have kind of a precise description that you're starting from. that precise description is what we've been trying to capture in the computational language we built. And that precise description is not that's not the kind of currency of LLMs. That's not what LLMs think about. It's not what humans think about. Humans don't get to run precise code in their brains, nor do LLMs. Humans, like LLMs, can call tools to do those things. That's the role of the computational language that we built. The role is to provide that solid formal foundation that can be interfaced with by humans. That's what we've been building it for all this time. Nowadays, it can also be interfaced by AIs and LLMs. And it's very convenient that the LLMs are sort of human-like enough that all that work that we put into making a good interface, a good design for our computational language, that just immediately translates to making it easier, not just for humans to understand, but for AIs to understand. And as one sees LLMs try and write Wolfram language code, the fact the systematic character of Wolfram language code is critical to the success of LLMs in being able to write it. And that's so I think the view that I have is we get to do things at a sort of talking level, vague level. We can do that with our own brains. We then in the past have had to formulate for ourselves how to make that precise. We now have tools that can help us to go from the vague thought to the precise formulation. And the thing is that precise formulation is the definition of what we're actually doing. So this idea of I just tell it to the LLM and just goes off and does it, and that's how we build science, that's not really, that doesn't really make sense, because what's going to be the sort of solid bricks that you can build up with, that's this precise stuff that's represented in computational language that in the past we might have represented with mathematical notation. Now we have this kind of computational notation to represent these things. That's kind of the story of how we expect to really build sort of exact science, so to speak, is by using this kind of computational notation. So I think that's the way these things fit together. And it's great to have this kind of new interface, new class of effectively users of the technology that we built. And it's a very kind of, it is complementary to LLMs as it is complementary to humans. I mean, people said when we first brought out Mathematica, for example, people said, oh my gosh, there are things that humans should have been doing. It's preventing, it's removing all this stuff that humans used to spend all this effort on. And it's like, that's a good thing, because that lets the humans go further, do more. And that's really how it's worked out, that humans now just have a tool that they can use. And so it is for the AIs and LLMs. Okay, maybe one last thing. Oh boy, interesting questions here, which I didn't have a chance to get to. There's a question from Jordan here. What's my opinion of ethical frameworks being applied to AI tools? What sort of ethics do you think should be applied when considering machine learning and AI tool research? First point is ethics is not kind of like science. Science has this foundational axiomatic idea that you can sort of do science in a modular way. You can say, I'm going to separate off this precise area, this precise kind of thing, and study it scientifically and figure out the whole story of how it works. Ethics doesn't really work that way. The question of, is it the right ethical thing to do this or that, will often entrain kind of the whole structure of our civilization. You kind of can't answer that without kind of the details of our whole civilization, so to speak. And certainly there's no sense in which there's an abstract ethics independent of kind of human characteristics. Ethics is kind of what we want it to be, so to speak, what fits in with our civilization, not something which is kind of a mathematical thing or a formal thing like of the kind that we're used to in some area like mathematics or theoretical science. Now, in terms of how to sort of do the right things, one of the challenges is that there's sort of this trade-off between knowing what the AI is going to do and making sure it always does the right thing, and letting the AI do things that only AIs can do, and do things that are sort of taking the best advantage of its computational capabilities. In terms of my concept of computational irreducibility, it's sort of a choice between having computational irreducibility, where you can't work out the consequence of the computation without basically just running the computation, and forcing you to have computational reducibility, where you can know things about what will happen and be sure nothing bad will happen, but where also you are, in effect, you are able to jump ahead of the computation. So the computation is not doing as much as a computation could do. It's kind of like, why are you doing the computation if you can just say what the answer will be from the computation without even doing it? So if it's like you really need to do the computation was really worth doing, then it's kind of inevitably irreducible, and that means that it is something that that you have to where you can't expect to know in advance everything that will happen. So I think there's, I've thought quite a bit about kind of how one might approach sort of ethics around AIs. I think that, a few hundred years ago, there was this moment when political philosophy became sort of important in the shaping of what became modern democracy and so on. We are back at a time when sort of the issues are different, and technology and AIs have driven a lot of that. And it's kind of like, so now what do we do? Now what do we want to do as a civilization and so on? And those are important questions, and defining what are the significant things about, whether it was, freedom and democracy and so on back in the day, or whether it's something, how one thinks about that, and how one extends that, how one modernizes and generalizes that to the world of AIs, and at what point the AIs have rights to be free themselves, and whether one allows freedom of thought for AIs as we have always done for humans, up to a point at least, and how that works. These are important questions which I'm not going to have time to talk about today, but I'm be happy if people want to ask about that in the future. I'd be happy to say what I know, which is still very limited. I mean, I have thought about these things, but I must say I think there are a lot of difficult questions which I haven't been able to address. And it's always the case, as one thinks about things like this, that sort of having a practical instantiation of the issues is important. Like when I was doing things a couple of years ago now with LLMs and so on, and I was thinking, okay, we can now connect an LLM to programs running on my computer. And it was like, before that, I'd kind of just ignored the question of, LLM security and things like this. And then I realized I'm about to connect an LLM whose functioning I don't understand to the file system of my computer. Something could go very badly wrong. What should I be telling it? How should I be determining what it's doing? The fact that I sort of brought it to that practical point was important for me to kind of understand even the conceptual point about how one should kind of limit the actuation capabilities of AIs and so on. So anyway, I think much more to figure out, some of which I hope will become a bit clearer as we practically implement things. I mean, like, for example, with our notebook assistant, there were things about that. I certainly imagined what that would be like. We've been developing it for the last couple of years, and it's been sort of gradually getting better. But the kind of the qualitative feeling of using it was not something I had expected in many ways. So one of the things that was interesting to me, I consider myself a fairly expert user of Wolfram language. It's still been very useful to me, but it's done another thing which I didn't expect. It's made me bolder in what I try to do. Because there are things where I have this thought, and it's like, I wonder if I could do that. Well, if I was doing it myself, it's like, yeah, it wouldn't take me that long, but it would take me 10 minutes. And it's like, well, let me just try asking the notebook assistant, and by golly, it does something interesting and useful. And then I'm kind of off and running, and I didn't have to make that 10-minute investment. I mean, one of the things that's been important to me in doing science is as tools get better, the level of things that one can do kind of on a whim gets bigger. For me, if somebody says, oh, there's some new kind of radiological system you could study, and it's like, so long as I know the definition, I'm going to be able to write code for it really very quickly, and I'm going to be off and running and investigating things, and that's something I can kind of expect to do on a whim. I'm not making a month-long investment to get to that point. And so it's important what gets to the level of do it on a whim type thing. And Notebook Assistant has brought more things into that domain, and that's been surprisingly important to me, even over the last few weeks that I've been using sort of the final version of it, or the version of it that exists today. It's going to get progressively better, even in the next few weeks, actually. That was an unexpected thing, and I expect I expect the unexpected in terms of when one actually gets tooling to a certain point that one can really feel what it's like to use those kinds of things. All right, I should wrap up here. It's probably my last live stream, is it, before the Christmas period and holiday period and so on. So thanks for joining me today. Happy holidays, and look forward to chatting with you another time. Bye for now. Oh, I should say, I got to say something. I think, see, this is where I'm just the CEO. I don't know all these things, but I think there's all kinds of interesting holiday promotions for all kinds of hobbyist products and interesting educational products and so on. And check them out. I wish I could tell you, like one of those shopping channels, I wish I could tell you more kind of chapter and verse of get this and this and this, but as I say, I'm just the CEO, and I don't know all those details. But I know that we've figured out a lot of interesting, cool things, and a good time to kind of get involved with all of this interesting technology and so on that we've been building. And anyway, look forward to chatting about it more in the future. So bye for now.